In the previous video, we learned that an input sentence is passed to the encoder as a sequence of vectors after going through embedding and positional encoding. Then, how does the encoder use these vectors to understand the overall context of the sentence? The key mechanism behind this is self-attention and its extended form, multi-head self-attention. In this video, we'll take a closer look at how they work. The figure shown here illustrates the overall architecture of the transformer, and the part highlighted in red corresponds to the transformer's encoder. The encoder is built by stacking n identical layers, and in the original paper, 6 layers were used. Each encoder layer consists of 2 sublayers, multi-head self-attention, and a feed-forward network. The output of each sublayer is processed with residual connections and layer normalization. Finally, the output of the last encoder layer is passed on to the decoder, where it is used in the multi-head encoder-decoder attention mechanism. Now, let's take a closer look at self-attention, the core operation of the encoder. Unlike RNNs, transformers do not process inputs sequentially or pass along hidden states. Instead, they learn contextual information through self-attention. In self-attention, each word in a sentence updates its representation by referring to all other words in the same sentence. For example, in the sentence, "I like baseball better," the word better computes its relevance to every word in the sentence, including itself, and assigns higher weights to the more important ones. Because this computation is performed in parallel for all words, the model can efficiently capture context even in long sentences. At the heart of this process are the 3 key components: query, key, and value. Now let's take a closer look at what query, key, and value. These are the core concepts for understanding self-attention in transformers. Query is a vector that represents the information to be retrieved from the input. Key is the vector that the query is compared against to determine how relevant another word is. Value is the vector that contains the actual semantic information of the relevant word. These Q, K, and V vectors are derived from the input vector X, which is the sum of the input embedding and positional encoding. More specifically, the input vector X is multiplied by different trainable weight matrices to produce Q, K, and V, respectively. It's worth noting that these weight matrices are randomly initialized at the beginning and are updated to optimal values during training. Next, let's walk through how self-attention is actually computed. First, we calculate the dot product between the query and key vectors for each word to measure the similarity between words. This is called the attention score. As the dimensionality of the vectors increases, these dot product values can become excessively large, so a scaling step is applied to stabilize their magnitude. Here, dk refers to the dimensionality of the key vectors, which is set to 64 in the original paper. Next, we apply the softmax function to these scaled scores, converting them into attention weights, which represent how important each word is in probabilistic terms. Finally, these attention weights are multiplied by the corresponding value vectors, and then summed together to produce a single weighted sum vector. This vector represents the result of integrating information that is distributed across multiple words in the sentence into a single contextual representation for a given word. Query, key, and value are the core concepts you need to understand self-attention in transformers. So let's break it down with a simple sentence. I like baseball better. First, we split this sentence into tokens, I, like baseball better. Now let's focus on the verb like and ask a question from its perspective. What do I like? That question is the query. In other words, the query represents what we're trying to find. Next is the key. The key represents the characteristics of each word. So, for example, I is a subject and a person, so it has low relevance. Baseball is an object and a target, so it is highly relevant. Better expresses comparison or degree, showing moderately relevant. By comparing these keys, the model figures out which words are more relevant to the query. Finally, we have the value. And here's an important point. The model doesn't just pick one word. Every word has a value, its own meaning, and these values are combined, but with different weights. So, like will take in a lot of information from baseball, some from better, and just a little from I. As a result, instead of just meaning like, it becomes more specific. Something like baseball better. In other words, words look at each other and refine their meanings. And that's exactly what self-attention in transformers does. Now, let's look at how self-attention is actually computed through a simple example. The sentence we'll use is, I like baseball better, which consists of 4 tokens. As in the original paper, each token is represented by a 512-dimensional input vector. So the entire input can be viewed as a 4 by 512 matrix X. We then multiply this input matrix X by 3 different weight matrices, WQ, WK, and WV, to compute the query, key, and value matrices. Each weight matrix has a dimension of 512 by 64, which transforms Q, K, and V into matrices of size 4 by 64. In other words, each word is projected from the original 512-dimensional space into a 64-dimensional space, specifically used for the attention calculation. The equations shown here illustrate the process of generating Q, K, and V by multiplying the input matrix X with WQ, WK, and WV, respectively. Using the previously computed 4 by 64 matrices Q, K, and V, we can now carry out the actual self-attention computation. First, the key matrix is transposed to a 64 by 4 matrix and then multiplied with the query matrix. This results in a 4 by 4 score matrix. To prevent the values from becoming excessively large, this score matrix is scaled by dividing it by root dk, and then the softmax function is applied. The result is a 4 by 4 attention weight matrix. Next, this attention weight matrix is multiplied by the value matrix, producing the final output matrix with dimensions 4 by 64. For example, if we look at the second row marked in red, corresponding to the token like, and its attention weights are 0.1, 0.2, 0.7, 0.4. The output vector is computed as a weighted sum of the value vectors. In this case, since the largest weight, 0.7, is assigned to baseball, the token like builds its contextual representation by relying most heavily on information from baseball. So far, the self-attention mechanism we've discussed computes relationships between words from a single perspective. However, words in a sentence carry much more than just basic semantic meaning. They also encode grammatical roles, sentence type, emphasis, and various relationships between words at the same time. Because a single self-attention mechanism has limitations in capturing all of these diverse patterns, the transformer uses multi-head attention. For example, in the sentence, which do they play better, soccer or baseball? One attention head might focus on words like which, do, and the question mark to recognize that the sentence is a question and identify its sentence type. Another head might focus on the relationship between play, soccer, and baseball to capture the semantic connection between an action and its objects. Yet another head might attend to nouns or emphasized expressions in the sentence. In this way, multi-head attention runs multiple self-attention mechanisms in parallel, allowing the model to understand a sentence simultaneously from multiple perspectives. Multi-head self-attention does not rely on a single self-attention mechanism. Instead, it runs multiple self-attention operations in parallel, allowing each head to learn patterns from a different perspective. In the original Transformer paper, 8 heads are used. Each head receives the same input, but because it uses different weight matrices, it learns relationships between words from its own unique viewpoint. This is similar to how different filters in a CNN learn different types of features. For example, one head may focus on grammatical relationships between words, another may specialize in identifying the sentence type, and a third may concentrate on emphasized expressions within the sentence. Simply concatenating multiple heads increases dimensionality and does not integrate information semantically. Output projection matrix combines the heads into a single meaningful vector, producing a representation suitable for feed-forward network. Using the same self-attention example as before, let's now see how multi-head self-attention works in practice. In the transformer, the model dimension is 512, and this is divided across 8 heads. As a result, each head operates on a 64-dimensional subspace, since 512 is divided by 8 into 64. This design ensures that when the outputs of all heads are concatenated, the overall dimensionality remains 512. The input sentence, "I like baseball better," is represented as a 4 by 512 input matrix X. In multi-head self-attention, instead of using a single set of weight matrices of size 512 by 64, the transformer uses 8 different sets of weight matrices WQ, WK, and WV, as described in the original paper. As a result, 8 separate 4 by 64 query, key, and value matrices are computed, one set for each head. Using the previously computed 4 by 64 query, key, and value matrices for each head, we now perform the multi-head self-attention computation. Since a total of 8 heads are used, the same self-attention operation is carried out in parallel on 8 different sets of Q, K, and V, each generated from different weight matrices. Within each head, the key matrix is first transposed to 64 by 4 and multiplied with the query matrix to produce a 4 by 4 score matrix. After applying scaling in the softmax function, we obtain a 4 by 4 attention weight matrix. Next, these attention weights are multiplied by the value matrix, resulting in a 4 by 64 output matrix for each head. As a result, we obtain one output matrix per head, yielding 8 output matrices in total. From the previous step, we obtain 8 output matrices, each with dimensions 4 by 64, one from each head. When these outputs are concatenated along the feature dimension, they form a single 4 by 512 matrix. However, at this stage, the heads are simply placed side by side. To semantically integrate the information learned by each head, this concatenated matrix is then multiplied by a final output weight matrix, WO. The dimension of WO is 512 by 512, and this transformation produces the final output with dimensions 4 by 512. Maintaining the same dimensionality as the input is crucial because it allows the model to apply residual connections, where the input and output are added together. In this sense, WO not only fuses information from multiple heads into a single representation, but also plays a key role in ensuring the structural consistency and stability of the overall transformer architecture.